The Carry-It-All minivan, a popular vehicle among soccer moms, obeys the demand equation. P equals negative 1/50th x plus 9,000. The cost of producing X vans is given by the function C of X equals 6,080x plus 20,000. Part A, express the revenue as a function of X. Express the profit P as a function of X. Find the value of X that maximizes the profit. What is the maximum profit? What price should be charged in order to maximize the profit? So we have a lot to cover in this problem. The first thing that I want to do is make sure that we understand this demand equation that we were given and the variables within that equation. So the variables in this equation are P. P stands for price. This is a lowercase p. And then we have the variable X. And here is X vans. X is the number of vans. And so this is an equation that relates the price to the number of vans. So we call that the demand equation. Then we have this capital C. Capital C is for cost. So they're giving us a function called cost that has the variable X. So this is the number of vans telling us the cost to produce those vans. We also have capital R. Capital R is revenue. And capital P, so it's a little bit confusing. We have lowercase p for price and capital P for profit. So we've got a lot of different variables and functions going on here. We're going to start with part A, and in part A we want to express the revenue, capital R, as a function of X. We have a business formula where we can calculate the revenue, and the revenue is X times P. And X and lowercase p are the variables that we described up here in the demand equation. Lowercase p is price, and X is the number of vans. So to find the revenue, we're doing the number of vans times the price. And we're going to use this demand equation to create that revenue function. So we're going to substitute in for price. So that's X times negative 1/50th X plus 9,000. We can distribute that X to get negative 1/50th X squared plus 9,000X. So we now have the revenue function. Now we need to do profit, express profit, capital P, as a function of X. There's another business formula for profit. And the business formula for profit is that profit is revenue minus cost. So we have just found the revenue function in the previous part, and we were given the cost function in the initial problem. So we're going to use the revenue function that we just calculated and the cost function to calculate profit. So we're going to do negative 1/50th X squared plus 9,000 X, and I can see I wrote over here 900X instead of 9,000. Okay, so we're doing revenue minus cost. We just wrote down the revenue. We're going to subtract the cost. I need to make sure that I subtract the whole cost function. So that's going to be minus in parentheses 6,080X plus 20,000. We are going to distribute this negative to both the terms in the cost function. That gives negative 1/50th x squared plus 9,000 x minus 6,080x minus 20,000. We have some like terms that we can combine. We have this 9,000x minus 6,080. So that will give us negative 1/50th x squared plus 2,920x minus 20,000. So this is our profit function, profit in terms of x. So now that we've built both the revenue function and the profit function, we're going to do some calculations with this profit function. We want to find the value of x that maximizes the profit and find what is that maximum profit. Let me write down that profit function for us a little bit larger. We have a profit function being negative 1/50th x squared plus 2,920x minus 20,000. We can see, because of the squared on the x, that this is a quadratic function. And we know that the graph of quadratic functions are a parabola. And this particular parabola has a leading coefficient that's negative. And so we will have a parabola that is facing down. Now this is significant for us because this parabola represents profit, and we're looking for the maximum profit. That maximum profit will occur at the vertex. So the calculation that we're going to do to find the maximum profit and what value of x gives the maximum profit is to find the vertex. We do have a formula for finding the vertex. The vertex is an ordered pair hk, and our formula for h is negative b over 2a. So in this function, we have a being negative 1/50, b being 2,920. So a is always the coefficient of the squared term, and b is the coefficient of the x term. So we have negative 2,920 divided by 2 times negative 150. That's negative 2,920. And 2/50 is going to reduce to 1/25, and that's still negative. So this is going to simplify to be 25 times 2,920. So 2,920 times 25 is 73,000. So we are going to need to sell 73,000 cars to get a maximum profit. Then we want to find what the maximum profit is, so we're going to substitute that 73,000 into the profit function. We get negative 1/50th times 73,000 squared plus 2,920 times 73,000 minus 20,000. These are really big numbers. So let's get our calculator out so we can show typing this in. And that will give us both parts of the question that we see in C. Okay, so here's our calculator. And we want to do negative 1/50th times 73,000 squared plus 2,920 times, we're going to do 73,000 minus 20,000. All right, so there would be our maximum profit. So we've got 10656 with 4 zeros. So let's put some commas in. So that is 106,056,000 for the maximum profit. So we are going to get, this is for part C, a max profit of 106,560,000 by selling 73,000 vehicles of these vans. So we've got one more part to go, and that's part D, and it says what price should be charged in order to maximize the profit. So we do have a function that we were given at the beginning. Remember that demand equation, which related price to number of vans. So let's write down that demand equation. So in part D, we're going to use lowercase p equals negative 1/50th x, and I think it is plus 9,000. This is the price related to the number of vans. The question says what price should be charged in order to maximize profit. So we've already figured out this number to maximize the profit, and that is the 73,000. So we're going to substitute in to the demand equation 73,000. So we have negative 1/50th times 73,000 plus 9,000. Let's get our calculators again. And we're going to do negative 1/50th of 73,000 plus 9,000. And that gives us 7,540. So we got that price that should be charged to maximize the profit to be $7,540. I want to come back to this really large number here, which is the maximum profit. I took a look more closely at the directions, and it said to round to the nearest millions. And this is the millions place here where that 6 is. So if we're going to round to the nearest millions, we need to look to the right of the millions place, which is a 5. So that means that we're going to round up. So if we round to the nearest millions, it would be 107 million would be the maximum profit. On this one, we want to find all vertical asymptotes and create a rough sketch of the graph near each asymptote. Our function that we're working with is f of x equals x minus 11 over x squared minus 121. So what you see in this blue box here is something that I pulled from our notes on vertical asymptotes. I gave some instructions here on how we're going to find any vertical asymptotes of a function. So when we're finding vertical asymptotes, if our function is a rational function like this, p of x over q of x, p of x and q of x have no common factors, and a is a 0 of the denominator. A being a 0 of the denominator means a is a solution to the equation q of x equals 0. Then a is a vertical asymptote of the graph of f. So these words are giving us guidance on how to find these vertical asymptotes. So the key part that I want to point out to you is that our rational function can't have common factors. So I've laid out some steps here to ensure that we have no common factors. We're going to start off by factoring the numerator and denominator, canceling out any common factors. So that's going to make sure we don't have common factors. And the solutions to q of x equals 0 are going to provide us with the vertical asymptotes. So we're going to set that new denominator equal to 0 and solve, and that solution that we come up with is the vertical asymptote. So let's follow these steps. We're going to start by factoring the numerator and denominator. Our numerator x minus 11 is already completely factored. The denominator is a difference of squares, so we're going to factor that as x and x. 11 times 11 is 121, and we're going to have a plus and a minus. So this does give us a common factor. We're going to cancel out that common factor of x minus 11, and we get 1 over x plus 11. So we've now taken our function. It had common factors. We got rid of the common factors. So now we're going to set the denominator, x plus 11, equal to 0, and solve. And we get negative 11 as the solution, and x equals negative 11 is the location of our vertical asymptote. So we found the vertical asymptote. It only has one. If you're wondering, what about this factor that we canceled out, that factor that we canceled out is a hole in the graph. So at x equals 11, there will be a hole in the graph instead of a vertical asymptote. So when there's a common factor, we get a hole. Now the last thing that we want to do here is to sketch what the graph will look like near that vertical asymptote. So if we sketch, we're going to put negative 11 on the sketch. And we know that based on the definition of the vertical asymptote, that the y is either going to go to infinity or negative infinity. So that is the definition of a vertical asymptote. When we have a vertical asymptote at x equals negative 11, by definition, we know that as x approaches negative 11, y will approach infinity or negative infinity. So we know that our graph at that vertical asymptote, we got some choices here. It will go to infinity on the right, or it might go to negative infinity on the right. on the left, it will go to infinity, or it might go to negative infinity. So when we sketch this, we have to figure out which one of these is happening. So this is a question mark. Is it going to infinity? Is it going to negative infinity? Is it going to infinity on the right or negative infinity on the right? So the way we figure that out is by testing around it. So on the left, excuse me, this is on the right, we're going to pick a number that is a little bit bigger than negative 11. So let's do negative 10.9. And we're going to test a value a little bit to the left of negative 11, like negative 11.1. And we're going to see what happens with our function. So remember, we simplified our function to be 1 over x plus 11. So I'm going to test it with negative 10.9. 1 over negative 10.9 plus 11. That's 1 over positive 0.1. And that is a positive number. And so that tells me that on the right, the y is going to approach infinity. So now, instead of a question mark over here, let me get rid of this question mark. I now know it's going to go to infinity on the right, and I can get rid of this one going to negative infinity on the right. And then we'll test the other side. F of negative 11.1, that's 1 over negative 11.1 plus 11. Now we have 1 over negative 0.1, and that's a negative number. So now on the left, I know it's going to negative infinity. So now on the left, we can get rid of this one going to positive infinity, get rid of this question mark, and we have now sketched the graph near that vertical asymptote. On the left, it's going to negative infinity. On the right of negative 11, it's going to positive infinity. Solve the exponential equation using the method of relating the bases by first rewriting the equation in the form b to the u equals b to the v. The equation we're working with is 1 over the fifth root of 16 equals 2 to the x. So before we start solving that equation, let's talk about this method that we're using of rewriting the problem as b to the u equals b to the v. When we write the equation in this format, we're going to be able to apply a property of exponential functions called the one-to-one property. And that property says if the y values are the same, the x values are the same. And so I can conclude that if b to the u equals b to the v, then u must equal v. So when the bases are the same, the exponents must be equal to each other. So that's our goal, for us to write the problem in this way so that we can apply this one-to-one property of exponential functions. So looking at our problem, I notice that on the right-hand side, I have a base of 2. And the number inside the radical is 16, which is a power of 2. So I'm going to be able to rewrite this equation to have a base of 2 on each side. So let's start by changing that 16. So the 16, so I start off thinking about 16, 2 to the second power is 4, 2 to the third power is 8, and 2 to the fourth power is 16. So I can write 16 as 2 to the fourth power. Then I notice that I have a radical, and all radicals can be written as powers. So the fifth root is the same as the 1/5 power. So I can write this as 1 over 2 to the fourth to the 1/5 power. Then there's a property of exponentials that allows me to simplify this right here. And the property that we're using is called the power rule for exponents. And when you have an expression like this, what we can do is multiply those exponents together using that property. So that would give us 1 over 2 to the 4/5 equals 2 to the x. And finally, there's one more property of exponents called, well, it doesn't really have a name. It's a property using negative exponents. And we're going to be able to bring that factor to the numerator using that property. So it's 2 to the negative 4/5. So when we move that factor to the numerator, it gets a negative in the exponent. So now we've achieved our goal up here of writing the equation in a way where we have the bases the same on both sides. Once the bases are the same, we can apply that one-to-one property and say that the exponents must be equal to each other. So we get negative 4/5 is equal to x, and we have solved the equation for x. So x equals negative 4/5 is our solution. Solve the exponential equation using the method of relating the bases by first rewriting the equation in the form e to the u equals e to the v. The equation we're working with is e to the x squared equals e to the x times e to the 12th. So we want to write our equation with the same base on both sides so that we can simplify the equation stating that the exponents are equal to each other. So this is a property, the one-to-one property, and we're going to be able to simplify saying that those exponents are equal to each other. So we're going to simplify on the right-hand side first. We have e to the x times e to the 12th. And we're going to use a property of exponents called the product rule. Let's try that again. Product rule. And the product rule for exponents looks something like this. If we have b to the m times b to the n, we're going to be able to simplify this to be b to the m plus n. So if we're multiplying expressions that have the same base, we're going to be able to simplify by adding those exponents together. And that's exactly what we have on the right-hand side of our equation. We're multiplying expressions with the same base, so we're going to be able to add those exponents together. So we get e to the x plus 12. On the left-hand side, we're just carrying that down, and you can see that we have the same base on both sides. We can apply that one-to-one property and say that the exponent on the left is equal to the exponent on the right. So we have x squared equals x plus 12. We're going to move all the terms to the same side. That's x squared minus x minus 12 equals 0. This is a quadratic, and we can solve it by factoring. We get x and x, 4 and 3. 4 times 3 is 12. We're going to do a minus on the 4 and a plus on the 3 to create the negative 1 in the middle. Now that we have it factored, we can set each factor equal to 0. And that gives us x equals 4 and x equals negative 3. And we have our solutions to that exponential equation, 4 and negative 3. Solve the exponential equation using the method of relating the bases by first rewriting the equation in the form e to the u equals e to the v. So in this question we have e to the x squared equals e to the 12th over e to the x to the 4th. So our goal is to write the equation in this format, e to the u equals e to the v, and once we get it in that format, we're going to be able to simplify the equation to u equals v. That's due to a property of exponential functions called the one-to-one property. So we have to use some other exponential properties as well so we can get to this point right here. So the first one I'm going to focus on is in the denominator here. So there's an exponential property called the power rule. And the power rule for exponents deals with this situation. When you have a base to a power, and then that whole expression is raised to another power. You can see that's the exact scenario we have. And when you have this situation, you multiply the powers. You get b to the m times n. So I'm going to start by simplifying that denominator to become e to the 4x. We multiply that x and 4 together to get 4x. Then we're going to simplify this whole right-hand side using another property of exponents called the quotient rule. And the quotient rule deals with this situation when you have b to the m over b to the n. You're dividing expressions with the same base. And when you divide expressions with the same base, you subtract the exponents. So that's what we're going to do in our example here. We have e to the x squared equals e to the 12th minus 4x. So we were able to apply that quotient rule. And now you can see that we have the bases the same on both sides. We can apply our one-to-one property and say that the exponents must be equal to each other. So x squared equals 12 minus 4x. So we have a quadratic equation. I'm going to move all the terms to the same side. That will give x squared plus 4x minus 12 equals 0. We can try to solve this by factoring. Let's see if that works. Okay, so our factors of 12 are 1 and 12, 2 and 6, 3 and 4. 2 and 6 might work. Let's try that. So we can have a 6 and a 2, and we would need the 6 to be positive and the 2 to be negative for it to factor properly. We're going to set each factor equal to 0, and that will give x equals negative 6 and x equals 2 as the solutions to our exponential equation. The population of a rural city follows the exponential growth model. P of t equals 2,900 e to the 0.34 t, where t is the number of years after 1991. What is the population of this city in 1991? What is the relative growth rate as a percent? And use this model to approximate the population in 2032. So before we start going over these parts, I wanted to pull this information from our notes from 5.1. This is the exponential growth model, or sometimes we call it population growth model. We have P of t equals P naught e to the kt. So it's important for us to think about what these variables stand for so we can understand it in the one that we were given up here. So P naught is the initial amount, the initial population of our city or whatever we happen to be talking about. So initial beginning amount. K is the growth or decay rate. So if your city is growing, it's called a growth rate. If it's decaying, it's a decay rate. And this value will be positive or negative based on the growth or rate. So positive when it's growth, negative when it's decay. T is time, and P is the population after some period of time. So they're referring to this P here. This P is the population after some period of time. So when we compare the function that we were given to our basic format, we have P of t equals 2,900 e to the 0.034t, we can see some comparisons to the variables that we have. So as the coefficient on e, we have 2,900. The coefficient on e is labeled here as P naught. So we know that 2,900 is our initial amount or our initial population. So since this question says that T is the number of years after 1991, this is our beginning point in time. And so part A is asking for what is the population of the city in 1991. That is our initial population. So the answer to part A is 2,900. In part B, it says what is the relative growth rate as a percentage. So we mentioned here that K is the growth rate. And let's use a different color. K is the coefficient of t, and we have the coefficient of t right here being 0.034. So K will equal 0.034. This question specifies that it wants it as a percentage, so we're going to move that decimal point 2 places to the right, and that gives us 3.4%. So this rural city has a growth rate of 3.4%. So that's the answer for part B. And then in part C, we want to use this model to approximate the population in 2032. So in 1991, we consider this to be our starting point, our beginning. And at the beginning, we set that to be a time of 0. In 2032, we want to approximate the population at that moment in time. So our time is going to be the number of years after 1991. So we're going to do 2032 minus 1991 to figure out how many years after 1991 it is. So 2032 minus 1991 is 41 years later. So that's our moment in time, 41 years later. So we're going to use our model. The population 41 years later is 2,900 e to the 0.034 times 41, and we'll get our calculators out for this one. And we're going to do 2,900 e to the 0.034 times 41. You notice that's all in the exponent. Your calculator might be different. You might need to put parentheses around that multiplication. And so we have 11,689. Let's go ahead and round that up because we have 0.7 and say that we have 11,690. So we're estimating that the population in 2032 would be 11,690. For this one, we want to find the domain of the logarithmic function. F of x equals log base 2 of -4 minus 5x. When we're finding the domain, we're finding out the values of x that we're allowed to substitute into this function, the values of x that will produce a valid expression for this logarithm, valid in the real number sense. So what we've learned about logarithms is that logarithms are only defined for positive values. So we've been able to see that log any base of a positive is defined. Log any base of a negative is undefined. And log base b of 0 is also undefined. So we only have a definition for logs when the expression inside the log is a positive value. So when we want to find the domain, we're going to take the expression inside the log, and we want that to be greater than 0. So greater than 0 means positive. And we're going to solve that inequality to find the domain on x. So we're going to add 4 to both sides. That gives negative x is greater than 4. Divide both sides by -5. Whenever we divide an inequality by a negative, we need to reverse that inequality symbol. And we're going to get x is less than -4/5. So the domain will be x is less than -4/5. We typically write that in interval notation. And with interval notation, I like to draw a graph first. And we're going to mark -4/5 with an open circle to say that -4/5 is not included. And the values that are less than -4/5 are to the left of -4/5, and those will be part of the domain. With interval notation, we need a lower bound. Now this arrow indicates that there is no lower bound, so we write -infinity, and an upper bound, and that upper bound will be -4/5. We use a parenthesis on -4/5 to indicate that it's not part of the set. So our domain is -infinity to -4/5. Another way to write the domain is using set builder notation. And with set builder notation, it looks something like this. We use curly braces to say we're talking about a set. We're talking about x's. X's are for the domain. And we want only x's that are less than -4/5. And we close out those curly braces. So that's another way to write the domain. Use the product rule to expand the logarithmic expression. Whenever possible, evaluate the logarithmic expressions. The expression that we want to expand is natural log of 8e to the 6th. So let's start off by recognizing this product rule. The product rule for logarithms looks something like this. You have log base b of m times n. So the reason why it's called the product rule is because you'll have a product inside your logarithm. And when you expand this, the way you expand it is to have log base b of m plus log base b of n. So you'll notice here that your factor of m went inside its own log, your factor of n went inside its own log, and we add those logs together. So this is the product rule for logarithms. You'll notice in our example, we do have a product inside of our natural log, and we're going to be able to use this product rule. So we'll write this as natural log of 8. That's the first factor. We're going to use plus, and we have natural log of the second factor, e to the 6th. So that step right there shows us applying the product rule to expand the logarithm. We also need to make sure that we evaluate whenever possible. We try evaluating when we have a number. In this case, natural log of 8 is a number, but it's not one that we can easily simplify. The reason why is because natural log ln is a log with base e. So we are able to simplify this log over here that has base e, natural log e to the 6th. Now there's lots of different ways that we can think about simplifying natural log e to the 6th. So let's try a few. So one way we can think about it is that natural log and e are inverse operations, and those operations cancel each other out, and you'll get just 6. Another way to simplify natural log e to the 6th would be to use the power rule for logarithms. The power rule for logarithms allows us to take this 6 from the exponent and move it to the coefficient. So we could write 6 natural log of e. And we know that natural log of e is 1, so we get 6 times 1 is 6. That's another way to simplify. One more way that we could simplify would be, all right, we've got natural log e to the 6th. You can say, I'm not sure what this equals. Let me say it's equal to some p. We know that natural log is the same thing as log base e. I'm going to write that as log base e of e to the 6th. And from here, I can rewrite the log as an exponential. So to do that, we start with the base. We have a base e. The log always equals the exponent, so that's going to be p. And then this expression is going to equal what's inside of the log. That's e to the 6th. Then we have e to the p equals e to the 6th. And we know that those exponents must be equal to each other by the one-to-one property. So p equals 6. And that expression, natural log e to the 6th, must equal 6. So we've simplified this as much as we can without a calculator. Well, I guess there are some other options as well, like the change of base formula, but we're going to leave it just like this. Natural log of 8 plus 6. Use the properties of logarithms to rewrite the given expression as a single logarithm. Whenever possible, evaluate the expressions. So we have natural log of x minus 4 squared plus natural log of 5x squared. So we're going to use our log properties to, I like to call condense. We're going to condense to a single logarithm. And the property that we're going to use is called the product rule for logarithms. So the reason why I know we're using the product rule is because of this plus sign between my logarithms. So the product rule looks something like this. Log base b of m times n equals log base b of m plus log base b of n. So the reason why it is called the product rule is because it has multiplication inside the log. So this multiplication turns into the sum of two individual logarithms. You use one factor in one log, the other factor in the other log. Now we're actually going the other way. We're starting with the sum of logs, and we want to turn it into a single log. So we do have the sum of two logs with the same base. We have the sum of this natural log and this natural log. Those have a base of e. And we're going to be able to condense this down to a single natural log. And when we condense it, we should use the product. We should use multiplication. So we're going to multiply x minus 4 squared times 5x squared. So we can write this as natural log. I'm going to use parentheses. X minus 4 squared times 5x squared. We might write that a little bit more conveniently as 5x squared times x minus 4 squared. The directions do say to evaluate when possible. I don't really see a ton of things that we can do to simplify here. We could multiply the squared out and use the distributive property, but I think this is much cleaner in the factored form. So I'm going to leave it as is. So we applied the product rule to condense to a single logarithm to get an answer of natural log 5x squared times x minus 4 squared. Solve the exponential equation e to the x equals 5. Now, there are three different main methods that I typically use to solve exponential equations. And the first one is to make the bases the same. And when you make the bases the same, you get something like b to the u equals b to the v, and you're able to simplify the equation to u equals v. Now this is a really nice method. Your answers look typically like nice numbers when you solve with this method, but it doesn't work all the time. You're not always able to make the bases the same. In this example, we can't make the bases the same. We have a base of e on the left, and on the right, we have a 5. We're not going to be able to match those two up. So although this method is really nice, it gives us clean answers, and it's typically simple to do, it doesn't work all the time. The other two methods for solving exponential equations are to convert to an exponential, and the last one is to take the log of both sides. These two methods, the answers don't look quite as clean, as nice. The answers are probably going to have logs in them. I apologize, I stated this incorrectly. This should say convert to a log. So your answers are not going to be as clean and nice, but you can handle a lot more exponential equations with these methods than you can with the first one. So we're going to try both of these methods to solve this exponential equation. So let's try the method of converting. So if we convert, we want to write it as a logarithm. So we're going to write log. We're going to use the base of the exponential as the base of the logarithm. So that's going to be base e. The log always equals the exponent. So the exponent that is attached to this base is x. So that log is going to equal x. And then the 5 is going to go on the inside of the logarithm. So we get x equals log base e of 5. We don't typically write log base e. We have special notation, which is ln of 5. So we have x equals natural log of 5. And we've solved the exponential equation. We get natural log of 5 as the solution. Now we can also use the other method, which is to take the log of both sides. So we start off with our equation, e to the x equals 5. I use natural log when I do this, so that if I need to use the calculator, it's a little bit easier to use. But you're actually allowed to use any base log that you want on this process. So I'm going to use natural log. I have natural log of e to the x equals natural log of 5. I'm going to use the power rule for logarithms on the left. That allows me to move that variable from the exponent to the coefficient of the log. So that's using the power rule for logarithms. And natural log of e is something that we can simplify. Natural log of e is 1. So we have x times 1 equals natural log 5. X equals natural log 5. So we've got the same answer using the other method. So we have our solution to this exponential equation to be natural log of 5. Solve the exponential equation. 3 times 6 minus 7 to the 6x minus 2 equals 10. So in order to start solving this exponential equation using the methods that we've learned, we really need to have this exponential portion isolated on one side of the equation. So we need to isolate this 7 to the 6x minus 2. So to isolate it, I'm going to get rid of this 3 first. This 3 is multiplied, so I'm going to divide. 6 minus 7 to the 6x minus 2 equals 10 over 3. I want to get rid of this 6 by subtracting 6 on both sides. That gives negative 7 to the 6x minus 2 equals, and let's combine these together. In order to combine the fractions, we need a common denominator. I'm going to leave the denominator of 3. Let's multiply by 3 over 3 to get negative 18 over 3. And when we combine those together, we get negative 8/3. I still want to isolate this exponential by getting rid of that negative, so I'm going to divide by negative 1 on both sides, and that gives 7 to the 6x minus 2 equals a positive 8/3. So now we have that exponential isolated, and we can think about using one of our methods, like making the bases the same. We can't do that here. Or we can convert it to a logarithm, or we can take the natural log of both sides. I'm going to take the log of both sides on this. So we can do natural log on the left. So that's natural log of 7 to the 6x minus 2 equals natural log of 8/3. We can now use the power rule for logarithms to bring that 6x minus 2 to the coefficient. So we get 6x minus 2 in parentheses, natural log of 7 equals natural log of 8/3. I'm going to use the distributive property and distribute this natural log of 7 to both terms. That gives 6x natural log 7 minus 2 natural log 7 equals natural log of 8/3. I'm going to add, my goal now is to try to isolate this x. So I'm going to add 2 natural log of 7 to both sides. That gives 6x natural log 7 equals natural log of 8/3 plus 2 natural log 7. And we're going to continue to isolate that x by dividing by 6 natural log 7 on both sides. That cancels the 6's and the natural log 7, leaving us with x on the left. And on the right, we have natural log of 8/3 plus 2 natural log 7 divided by 6 natural log of 7. Let's take a moment and practice typing this in the calculator in case we need to approximate our answer. I'm going to need parentheses around the whole numerator and parentheses around the whole denominator. So let's put those in. I'm going to put parentheses here and parentheses here so our calculator knows what to divide. So we're going to do natural log, and I already forgot what I just said. I need parentheses around the numerator, parenthesis, natural log of 8/3 plus 2 natural log of 7, close parentheses, divided by, and I need parentheses around the whole denominator, so that's 6 natural log of 7, and I'm closing parentheses for the log and the denominator. So we get an approximation of this answer. Let's round it to 3 decimal places, 0.417. So this is the exact answer with the logs, and this is the approximation. Thank you for checking out my videos. Have a great day.